Okay, welcome. I'm Fabio. I work for Logical Clocks. And in this presentation, we're going to discuss real-time feature engineering with Apache Spark and Off. We're going to discuss feature engineering, real-time feature engineering in the context of feature stores. Feature stores are a hot topic nowadays in the MLOps space. We have several talks in previous Spark Summit editions regarding the feature store. But to summarize it, essentially, the feature store is a repository for curated machine learning features, which are ready to be used by data scientists, both for training models and also for serving them in productions when the models is being served. There are a lot of reasons why you want to have a feature store in an enterprise. The main reason I would say is that you want to ensure consistency between the data that you use for training and the data that you use that you are serving to enrich inference vectors before sending them to the model for predictions. There are other reasons why you want to use that for governance, for instance, to speed up development process when it comes to generating new models and training new models, but also as a centralized place for storing metadata, storing statistics, and tagging and building up a catalog of features and so on. As I was mentioning, we have like previous talks that you can go more in details that you can look at. But essentially, the concept of feature store builds on a dual database setup, where basically you have a large data warehouse-like database. It can be Apache Hudi, it can be Delta Lake, it can be Apache Hive or a plain S3 bucket, where you basically store the bulk of your feature data that you can use for training new models. And on the other hand, you have low latency real-time database, like in the case of OpsWorks is MySQL DB cluster. We can use Cassandra or others, essentially to serve the same features live in productions. There is though one case, one use case that we have encountered several times when working with customers is essentially a real-time feature engineering problem. The previous setup, the dual database setup, requires data to be known in advance, so it can be featureized and it can be cached in the two databases. In this specific case, the data is not known in advance. It's actually sent by the client at the moment that the client needs to do the inference request. So we cannot be pre-computed, it cannot be stored, and it needs to be processed real time. The reason you want to do this processing is that you have to basically make sure that the data sent by the client is actually consistent with what the model expects. For instance, you might want to do one-hot encoding of some features. You might want to scale those features, numerical features down so that you achieve numerical stability, or you might want to do Windows aggregates over, for instance, the number of transactions a user has done in the past X minutes, for instance, or past hour. Additionally, this is a good point where basically the client does not necessarily knows all the feature vector that needs to be sent to the model, but like all their pipelines might be filling the rest of the vectors. And so the data coming from the client needs to be joined with data coming from the online feature store. There are a bunch of more requirements to make the problem more interesting. One is essentially you want to hide from an architectural point of view all the complexity from the clients. Clients might be deployed in different settings, so the simpler they are, the better they are maintainable, let's say. Most of these use cases from our experience are user-facing. So essentially, you need to have strict SLAs in terms of latency for computation and feature engineering jobs so that these features can be sent to the model and eventually sent back to the client. And additionally, always on the topic of hiding complexity, you want to avoid doing any feature engineering in the client itself. For the same reason, you need to be able to ensure consistency between what the client sends to the model and what the model expects. And if you have hundreds of clients out there that are making requests and they need to be all consistent with the model that you're currently serving, that becomes an impossible task. So there are different ways you can sort of achieve the real-time feature engineering using Redis. The first way we're looking at is actually the transform module of the TensorFlow package. Essentially, when you build a model in TensorFlow, you can package it and you can define what's called a signature function. That's what the model expects in as an input. But you can also define a preprocessing function. Essentially, the vector, when it comes into the model for prediction, it goes through this preprocessing function, and that can be a place where you can do some simple feature engineering, essentially. There are some drawbacks of this approach. One is this code is actually packaged together with the model. So you don't really have any visibility of what the model is actually doing in terms of preprocessing. You can't also reuse the same preprocessing function over and over in different models on different versions of the same model. So it becomes a bit tricky to keep to reuse and keep track of them. The other two issues are this: the processing function is executed on every single vector coming in. So there is no concept of state, and there is no concept of windows, and it's impossible basically to do aggregations over multiple requests coming in. And this is also a single-threaded operation, which means that it doesn't really scale with like lots of features being available. Another solution could be to use KF serving transformers. Essentially, KF serving is a set of tools that allow you to basically deploy models on top of Kubernetes. It's part of the Kubeflow family. And one of these components is actually a transformer. The idea is that you implement the Python interface you can see on the right side. And you can run Python code to actually do the transformation. Again, there are some downsides also here. The main one is that you are rewriting the pipeline to transform the data to do the feature engineering process. Essentially, you're going back of like before having a feature store where you have like different code for transforming features for training and transforming features for serving. There is also, doesn't scale with number of operations, sorry, number of features. It's not possible. Again, it's a single, the input are processed one by one. So there is no concept of like aggregations and windows and so on. And it doesn't come out of the box with support for fetching features from the online feature store and join them together. And at the same time, the data gets preprocessed, gets sent to the model, and that gets thrown away. So there is no easy way to actually save this featureized data to be reused later. The third approach, which is what we actually have been building, it's called Off. We try to basically solve all the issues mentioned before in this Off service. Essentially, Off is a service, is a backend service that runs and accepts requests from from clients. The preprocessing is not done on Off itself, but it's done on a Spark streaming application. So you can write your own transformations, and you can reuse the code both for training and both for generating data for training, but also for real time. Essentially, you can write basically pretty much PySpark. You can write Pandas UDF. You can write Java code. Off comes with first-class support for joining real-time feature engineering data with data coming from the online feature store. And it's also a pluggable architecture in a sense that allows you to, and we'll see later, allow you to basically extend the architecture to save data and so on and so forth. So in details, Off is basically a gRPC HTTP endpoint. Clients submit these requests. The client itself is mostly stateless. The preprocessing, as I was saying, is not done by Auth itself, but is offloaded to a Spark application. The stateful part is actually only to manage the routing of messages. We will see later on the message queue, but essentially you can have as many Auth instances running in parallel. We run them on Docker container on Kubernetes, so you can scale them up and down depending on the load. What essentially briefly Auth does is sends requests to a message queue. In OpsWorks, we use Kafka, but it can be extended to support managed services like the one provided by Amazon. The message is sent to a queue. On the other side, there is a Spark streaming application reading and doing the pre-processing, the feature engineering, and then the messages are sent back on another queue, and Auth pick them up and send them back to the user. In more details, if we look at how the messages are sent around, essentially, if you see the diagram on the right side, user sends a message to Auth. There is for each transformation that we have registered in our feature store, there is one Kafka topic which essentially acts as an input topic for the Spark application, and in the example is the middle one. And then there is one topic for each running Auth instance. Auth itself uses the OpsWorks REST API to basically manage the life cycle of the topics. So it starts them and stops them, adds them and removes them when new instances are added to the pool, basically. When Auth instance receives a request from the user, figures out which transformation the user wants, sends it to the correct Kafka topic, and when it does that, it encodes the instance itself in the key of the message, so that on the other side, the Spark application knows on which to which topic it sends it back. On the other side of the brokers, of the topics, there is a Spark application running. One point is that at this point, Auth does not enforce any schema on the incoming data. That allows for two things. First of all, it saves us to do one additional deserialization, reducing latency. And second of all, allows us to reuse the same Auth instances across multiple transformations. So we can scale the number of instances independently of the Auth instances independently from the number of transformations that you are currently running on the feature store. On the other side, as I was mentioning, there is a Spark streaming application. Now here, it really depends on what you're trying to do. If you are doing self-contained transformations, so in the example before, you are processing one by one, you can potentially have multiple Spark applications running at the same time, pulling data from the same Kafka topic, so that you basically achieve HA and you improve throughput. If you are doing more complicated stuff, like if you are actually doing processing, Windows processing and so on, then you need the state and you need to maintain the state. But at that stage, you can potentially split the transformations over multiple applications and have them anyway consuming from the same topic. The only difference is how you set up basically the consumer group. And finally, once the transformation has been applied, the Spark application knows which Auth instance generated this message because it's encoded in the key, and it sends back to the correct Kafka topic. Auth instance picks it up and sends it back to the user. We have a demo later on, and we can see exactly how the API can actually work in that sense to help out with this message routing and so on. As I was mentioning at the beginning, the Auth architecture is actually pretty. It can be expanded and extended with the dons. We do have support for some of the dons out of the box. Some of them can be written by the user themselves. One of the things you can achieve is basically you can save incoming data, so feature data coming in for feature transformations on an S3 bucket or on an OpsFS dataset. The reason you might want to do that is because that in the future you might decide to do additional transformations on those data, and that can help you to basically as a source of data or raw data. You might also want to save the transformation, the data transform themselves, the data after transformation. The reason you want to do that is for auditing, for instance. So any given time, you can go back and see exactly what your model was predicting on. But you can also save it for generating new trained data set in the future. So what you can do, you can basically save the data coming in, save data featureized, and leave empty basically the label, the prediction that is going to be filled in later on down the road when the prediction actually becomes known. In Opsos, you can save this data in a cache feature group backed by a Hudi table. So it allows you to later, like in a month time, 2 months time, whatever, allow you to go back and do an upsert on the table and fill in all the labels that you have discovered, basically, and that becomes a nice source of data or label data that you can use for train new models. And finally, this is a good place also for looking for data drifts. Basically, data coming in, the Spark application has access to the trained data set statistics. So at any given time, it can compute if the distribution of the data is somehow drifting away from the expected, from which the model has been trained on. And at that point, you can decide if you trigger an alert or essentially trigger a new training for a new model. This is what the API looked like in terms of from a client perspective. As you can see, as I was mentioning before, when there is the possibility of joining together online and streaming, and we'll see later the API for that. This one is only the streaming section of the API. You can specify a transformation that you want to apply. Again, off supports is independent from the transformations that you have registered on the feature store. You have to specify which one you want to apply, so that off is able to discover the specific Kafka topic to which to send data. And then you basically have to pass the data itself. It's just a JSON file. It's free form, and the application on the other side will ensure that the data is actually matches the expected input data. From an application perspective, you can we have two aspects. One is the feature group definition. Here we basically the top part we are basically defining a function, and we are basically registering this function with the feature store so that we are able later on to retrieve it and execute it. Basically, here we have a bunch of parameters you can pass in the create streaming feature group method, mainly if it's a batch, so it's a continuous and a bunch of configuration for the feature group itself. And on the other side, we have the processing itself. So when you're actually running the code and the method itself, you basically get the code from the feature store, and you call apply on the transformation. Sorry, you call apply on the feature group. And that basically triggers and set up the job and make sure that the messages are routed correctly on different topics and so on and so forth. So that removes and hides away all the complexity of essentially setting up all the routing that I was showing before. As I was mentioning, not all the data needs to come from the client itself, and most of the cases this is not true. So most of the cases, the client needs additional data from the online feature store. And the way actually we do it with Auth is basically Auth is responsible for on behalf of the user fetching the data to the online feature store. So if you see the diagram before on the right, you can see that we have an additional Spark pipeline reading data from S3 bucket and writing on MySQL Cluster, which is the online feature store for the Opsox platform. And if you look at the transformations If you look at the request that the client now sends, if we want to join different features coming from both streaming and online, the client now provides also an online section that allows the user to specify which trained data set to use as a base for the features. So in OpsWorks, when you create a trained data set, we save all the features from which feature groups they come from and in which order they are present in the feature vector, so that we don't break the model basically. So here you basically can specify that you want the user specifying that you want data from the fraud model version 1. You can specify a filter allowing you to select exactly like for which, in this case, for which customer, but essentially for which primary key you want the data from. You can also specify, it's not shown here in the UI in the slide. You can also specify a specific model. If you have trained a model in OpsWorks with provenance, we can figure out automatically and implicitly which trained data set was used to train which model. So you can also specify a specific model that you want to use as an online source of data. So in this demo, we're going to see how we can use the API presented before applied on a specific use case. So the use case here is trying to predict frauds in credit card transactions. We have a bunch of notebooks, Jupyter notebooks that we can use to see the APIs in action. We can start from the last one, which is what is supposed to be like this notebook represents the client itself. So this is what the client is going to be sending to the backend service. In particular, this is a section with data itself. This is what the client knows, the category, the date, the credit card, and the amount that has been used, has been spent. So this is what is going to be sent to the actual off endpoint for transformation. The transformation itself is provided as a separate notebook. Here we are, for the sake of the demo, we are using a Jupyter notebook, but on actual platform, you can provide transformations as a jar file or a Python file, and transformation can be pushed from an external CI/CD pipeline, for instance. So you can keep your code for transformation committed on a Git repository. The notebook itself is fairly simple. We are on top of doing a bunch of imports. We are establishing a connection with the OpsWorks feature store. And this is the transformation, one of the transformations for one of the feature engineering step. Here we are basically one of the encoding the category feature, checking if it's a personal care, travel, tech. This is going to be outputted and returned to the client for inference. As I said, there can be multiple of them, so we can wrap around into this transform function. Transform function needs to expect a data frame and epoch ID. This is what is going to be called by the API, by the HSFS API in the actual application, in actual streaming application. At every batch that comes in to the Spark streaming, basically. And finally, we register this code as a streaming feature group. We give the name, give it a version, and we actually save it. What the save does behind the scenes does a bunch of things. One of the things is we can actually save the notebook, the specific version of the notebook in the OpsWorks platform itself. And this allows for two things. The first one is you are always able to see what code the transformation is running. And the second one is to be able to retrieve this notebook, and the notebook can be converted into a Python file, and the Python file is then attached to the application doing the streaming transformation itself, basically. The second thing it does is also set up a bunch of topics, actually one single topic. This is the topic that the auth is going to push data to, and the Spark streaming application is going to consume data from. Just wanted to mention that all of this is actually monitored. We have dashboards alerting set up for either Kafka and also for the Spark application themselves. Here nothing has been pushed in Kafka for the past 5 minutes, so there is nothing really to show. But in this way, you can always control that your application is correctly saving and correctly applying transformations.
So we have a final notebook, which is the apply notebook. This is the actual notebook. It does that actually set up the Spark streaming application and does the actual transformations. So the notebook is very simple as well. The top is the same. So basically setting up a connection with the OpsSource feature store. Here we are fetching both the streaming feature group and the cache feature group. What I did, I basically created the same feature group both in streaming and the cache version. The reason for that, if you remember before, I was mentioning how you can extend the auth architecture to be able to save the transformations, on a cache feature group, so that you can use them later for training new iteration of the model, basically. So that's what actually we are doing here. So on the streaming feature group, we are calling apply, and we are passing the cache feature group as an additional output, basically. We are also passing a bunch of a dictionary with a bunch of arguments, and in this case, it's only one. These arguments are going to be provided to the Spark application when setting up the stream itself. In this case, we are passing the group ID. So basically, the idea is that because the transformation is stateless, I can run multiple instances of this notebook in parallel, and if I put them on the same group ID, then basically each message coming in will be processed only once by either one of the instances of the notebook running. So this is how the transformation looks end to end.
Okay, thank you for listening. You can look at the code for all the repository at github.com/logicalclocks. You can follow us on Twitter, and you can visit OpsSource.ai to try out the OpsSource platform and to play around with it. Thank you very much.